Today we're going to discuss the notion of the parity of a permutation. We start with the following definition. So given a permutation sigma of length n, a pair ij where I and j are between 1 and n and I is less than j is called an inversion if, well, we have I is less than j and sigma of I is greater than sigma of j. Let's consider the following example. So let's take sigma to be the following permutation in S6. Say we have 3, 1, 6, 5, 4, 2. Now, what are the inversions in this permutation? So here, for example, we see that 1 is less than 2, but sigma of 1, so we have 1 is less than 2, but sigma of 1, which is 3, is greater than sigma of 2, which is 1. So this tells us that the pair 1, 2 is an inversion. Then if we look at the pair 1, 3, then it's not an inversion because 3 is less than 6. When we look at 1, 4, it's not an inversion. 1, 5 is not an inversion, but 1, 6 is an inversion, right? So here 1 is less than 6, but sigma of 1, which is 3, is greater than sigma of 6, which is 2. Then what are the inversions with 2? So 2, 3 is not, 2, 4 is not. Well, it's actually 2 goes to 1, so this means that there are no inversions with 2 and higher indices. So if we take 3, then sigma of 3 is 6. So this means that everything else, like 3, 4, 3, 5, and 3, 6, are going to be inversions. So we have 3, 4, 3, 5, and 3, 6. Now, let's look with the 4. So 4, 5 is an inversion. And 4, 6 is also an inversion. And finally, 5, 6 is an inversion as well. So this is the list of all inversions in this permutation. So let us count of them. So how many inversions do we have? So we have 2, 5, 7, 8. So here we have 8 inversions. Let us draw a diagram for this permutation. So we have 1, 2, 3, 4, 5, 6. And we have 1, 2, 3, 4, 5, 6. So 1 goes to 3. Then 2 goes to 1. Then 3 goes to 6. 4 goes to 5. 5 goes to 4. And 6 goes to 2. So what we can see here is we can see that the inversions tell us whether the arrows originating from I and j would cross or not, right? So if I is less than j, but sigma of I is greater than sigma of j, so this means that the arrow that goes from I and the arrow that goes from j will cross. So for example, so here, so this crossing corresponds to this inversion here. Then the 1, 6 inversion will correspond to this arrow crossing. So we have an arrow that goes from 1 and an arrow that goes from 6, so this will cross. So 3, 4 is this crossing, 3, 5 is this crossing, 3, 6 is the crossing, well, here. Then 4, 5 is this crossing, 4, 6 is the crossing right here, and finally 5, 6 is the crossing here. So what we can say is that the number of inversions is equal to the number of arrow crossings. So this would be the geometric interpretation of inversions. And of course, so here when we make this analogy, we assume that all arrows are monotonic. So this means that they go either from right to left or from left to right, but they don't do these zigzag patterns. Now we can define the parity of a permutation. Definition. The parity of a permutation sigma is defined as -1 to the power, which is number of inversions in sigma. And we call permutation sigma even or respectively odd if the number of inversions in sigma is even or respectively odd. So this permutation here has 8 inversions. So this means that the sigma is even, and the parity of sigma, well, the parity is denoted as -1 to the power of sigma. And here, for this permutation sigma, it's +1. So this permutation has an even number of inversions, and because of this is an even permutation. In this lecture, we're going to establish some important properties of the parity of a permutation, and we're going to study the structure of permutations using the concept of inversion. In our previous lecture, we introduced the notion of a cycle. So this is a permutation that moves a certain sequence in a cyclic pattern. We define a transposition as a cycle of length 2. So this means, so this is a permutation that swaps 2 elements A and B. Now let's give an example. So let's consider cycle 3, 5 in S6. So let us write this transposition in our conventional notation. So we have 1, 2, 3, 4, 5, 6. And so here, so this transposition will only move elements 3 and 5. And it will move 3 to 5 and 5 to 3. And everything else doesn't move. We will need one more definition related to transposition. An adjacent transposition is a permutation of the form I plus 1. So this is a transposition that swaps 2 adjacent elements. So for example, a transposition 3, 4 would be adjacent, while 3, 5 is not adjacent. We state the following theorem. Every permutation sigma in Sn may be factored in a product, and the product in symmetric group is the composition of adjacent transpositions. Now, if sigma is the identity element, so the identity transposition, then we still consider that this theorem holds with an empty product. If we have an empty sum, then it's natural to say that its value is equal to 0. By analogy, the value of an empty product is equal to 1. And in the context of the group theory, the natural convention that an empty product of elements of a certain group is equal to identity element. And this convention will cover the statement of this theorem for sigma equals to identity element. We're going to prove this theorem by induction on the number of inversions in sigma. So the basis of induction is the case when sigma has no inversions. So what does it mean? So this means that for all I less than j, sigma of I is going to be less than sigma of j. So this means that the sequence, so sigma of 1, sigma of 2, all the way up to sigma of n, so this sequence must be monotonic. And so in particular, so this will tell us that sigma of I must be greater or equal to I, because this sequence is monotonic. And then we see that the only permutation with a monotonic sequence, sigma of 1, sigma of 2, up to sigma of n, is the permutation sigma, which is the identity permutation. And so thus, for the identity permutation, the claim of this theorem holds because we take the empty product of adjacent transpositions. And this establishes our basis of induction. So if sigma has no inversions, then it is the identity permutation, and the theorem holds trivially. Now let us do the step of induction. So to do the step of induction, we make our induction assumption. So suppose sigma has k inversions. So what is our induction assumption? So we assume that every permutation mu with k minus 1 inversion factors as a product of adjacent transpositions. Now, so we assume that every permutation with k minus 1 inversions factors in the pattern that we wish to establish. And now we need to prove that a permutation sigma with k inversions also will have a factorization into adjacent transpositions. So if sigma has k inversions, which is greater than 0, then it has an adjacent inversion. Of the form I plus 1. So otherwise, the sequence sigma of 1, sigma of 2, dot, 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 sigma of n is monotonically increasing. And so this could happen only when sigma is the identity permutation. Now consider the permutation mu, which is the product of sigma with adjacent transposition I plus 1. Now let us look at the diagrams of these permutations. So here we have I plus 1, and the fact that I and I plus 1 in sigma form an inversion. So this means that these arrows from I and from I plus 1 will cross. Now let us construct the permutation mu by taking this product. So first we apply the transposition I plus 1, and so then we apply transposition sigma. So this transposition will swap elements in I and I plus 1. So this means that here we have these two arrows going like this. And everything else is not changed. So this means that everything else will have vertical arrows. Now, let us compare inversions in sigma and mu. So in sigma, we had an inversion I and I plus 1. But when we take mu to be this product, then we see that in this product mu, I and I plus 1 is no longer an inversion, because now I will go to the left and I plus 1 will go to the right. So we resolve this inversion of I and I plus 1. So what we say is that I and I plus 1 is inversion in sigma, but not in mu. Now let us look at other inversions in sigma. So if we have an inversion AB, so inversion in sigma, where A and B are not in the set I and I plus 1, so then we can see that this implies that the same AB will be inversion in mu as well. So here we see that if we have A and B in sigma and these arrows will cross, then the same arrows will cross in this composition too. Now, what if we have an inversion where one of A and B is I or I plus 1? So if we have I, B, so an inversion in sigma, so this happens if and only if I plus 1, B is an inversion in mu, and I plus 1, B, an inversion in sigma, if and only if IB is an inversion in mu. So these claims can be either seen geometrically from this diagram or can be verified from the following relation. So we say that mu of j is equal to sigma of j if j is not equal to I or I plus 1, and then mu of I is equal to sigma of I plus 1, and mu of I plus 1 is equal to sigma of I. Right? So this we see that mu of I has the same image as sigma of I plus 1, and mu of I plus 1 has the image which is sigma of I. And these claims follow from these relations. So what we see here is that mu resolves precisely one inversion in sigma. So namely, I and I plus 1 was an inversion in sigma, but it's no longer an inversion in mu. And for all other inversions in sigma, we have one-to-one correspondence between inversions in sigma and inversions in mu. Now, our conclusion is that if sigma had k inversions, then mu has k minus 1 inversions, one less than sigma. Now, let us do a little bit of algebra. So we have that sigma times adjacent transposition I plus 1 is equal to mu. So let us multiply both sides of this equality by I plus 1 inverse on the right. So then we get sigma times I plus 1 times I plus 1 inverse is equal to mu times I plus 1 inverse. Now, on the left, so this product will cancel, and we get sigma times identity, or just sigma. And on the right, so let us think, what is the inverse of a transposition? So in this transposition, swaps elements I and I plus 1. To undo this transposition, we swap these two elements once again. So what we get is that the inverse of any transposition is itself. So this is actually true for all transpositions and not just adjacent transpositions. But here we need this fact for adjacent transpositions. So what we get is that sigma is equal to mu times adjacent transpositions I plus 1. But let us look at our induction assumption. So we assume that any permutation mu with k minus 1 inversions factors as a product of adjacent transpositions. And this mu has k minus 1 inversions. And so now if we replace mu with a product of adjacent transpositions, then the conclusion will be that sigma is a product of adjacent transpositions. Now we can give the following corollary of the proof. If we analyze the proof that we gave, then we can give a more precise statement. So if sigma has k inversions, then sigma may be factored as a product of k adjacent transpositions. So indeed, we saw that in our proof, so if sigma had k adjacent transpositions, then it can be written as a product of mu, which has k minus 1 adjacent transposition, times 1 adjacent transposition. And then by induction assumption, mu can be factored as a product of k minus 1 adjacent transpositions. And so then we get the factorization of sigma in k adjacent transpositions. Let's do the following exercise. Factor the following permutation sigma. So 1, 2, 3, 4, 5. That goes to 2, 4, 1, 5, 3 into a product of adjacent transpositions. So we start with our permutation sigma. 1, 2, 3, 4, 5, 2, 4, 1, 5, 3. And we look for adjacent inversions. So what do we have here? So 1, 2 is not an inversion. And 2, 3 is an inversion. So here we have 2, 3 is the adjacent inversion. And what we want to do is we want to factor sigma as some permutation mu times the adjacent transposition 2, 3. Now, what this rule tells us, that if sigma and mu are related by a product by adjacent transposition 2, 3, so this tells us that mu of 2 is equal to sigma of 3, and mu of 3 is equal to sigma of 2, and everything else is unchanged. So this means that we interchange here this 4 and 1. So sigma mu of 2 will be 1, and mu of 3 will be 4. And everything else is unchanged. So now we look for adjacent inversion in mu. And here we see that we have an inversion 1, 2. So this will be adjacent inversion. So now we factor out the transposition 1, 2 out of mu. So what will we get? So we have 1, 2, 3, 4, 5. So we now multiply this by 1, 2. And we keep the factor of 2, 3. Now, multiplying on the right by 1, 2 corresponds to swapping these two entries here. So this will be 1, 2, 4, 5, 3. Now, in this permutation, we have only one adjacent inversion. So this will be 4, 5. So let us factor out this adjacent transposition. So what we get is now 1, 2, 3, 4, 5. And so the bottom row will be 1, 2, 4, 3, 5 times 4, 5. And we keep everything else that follows times 1, 2 times 2, 3. And finally, so we see that this permutation is actually a transposition, adjacent transposition 3, 4. So what we get is we get the factorization that sigma is equal to 3, 4 times 4, 5 times 1, 2 times 2, 3. And if we check, then we can see that in this permutation sigma we had exactly 4 inversions. And now we obtain the factorization of sigma into 4 adjacent transpositions. So keep in mind that our multiplication is non-commutative, and so we cannot swap the factors 1, 2, and 2, 3 here. And in some of these factorizations, we could have the same factor 1, 2 appearing twice in different places. But this wouldn't mean that we can cancel the factor 1, 2 that appears twice. Now, let us tie the calculations that we have done with parity. So here we have the following proposition. If sigma is equal to mu times I plus 1, then the parity of sigma is opposite to the parity of mu. Now, this says that if mu had an even number of inversions, then sigma will have an odd number of inversions, and vice versa. So the proof of this is based on the observation that we already made. That so if I plus 1 is an inversion in mu, then sigma has one less inversion than mu. So if I and I plus 1 is an inversion in mu, then multiplying mu by I times I plus 1, so we'll resolve this inversion and keep the number of all other inversions the same. And if I plus 1 is not an inversion in mu, then sigma has one more inversion than mu. So this means that either we resolve an inversion, or on the contrary, we create an inversion. And so what we see that the number of inversions in sigma is either one less than in mu or one more in mu. And but then for parities, so if mu had an even number of inversions, then sigma will have an odd number of inversions, and vice versa. And then we get this relation for the parity of sigma and mu. Now we get the following corollary. So if sigma is a product of k adjacent transpositions, then the parity of sigma is equal to -1 to the power of k. So if sigma is a product of even number of adjacent transpositions, then the parity of sigma is equal to +1. And if sigma is a product of odd number of adjacent transpositions, then the parity of sigma is equal to -1. So we note that this factorization into adjacent transpositions for a given permutation is not unique. We can obtain different factorizations of sigma into products of adjacent transpositions. And these factorizations could have even different lengths. But what this says is that the parity of the length is preserved here. So we cannot obtain for the same permutation a factorization into 5 adjacent transpositions and into 6 adjacent transpositions. Because we know that the parity of a permutation, which is well defined, must be equal to -1 to the power of k, where k is the length of this factorization. So if sigma is even, then we can obtain only factorizations with an even number of adjacent transpositions. And if sigma is an odd permutation, then we can only obtain factorization with an odd number of factors. Now let us prove this corollary. So suppose sigma factors as a product of k adjacent transpositions. So here, so TJs are adjacent transpositions. So we can insert an extra factor on the left. We can multiply by identity element. So this will not change anything, right? So because multiplication identity times x is equal to x. But now this identity permutation is even, because identity permutation has 0 disorders, and so it's an even permutation. And then we have this proposition that says that if we take any permutation and multiply it by adjacent transposition on the right, then the parity of the product is opposite to the parity of the permutation. So when we multiply by first transposition, so the parity will switch from even to odd. When we multiply by second transposition, for this product, the parity will switch to even, and so on. And so then we obtain the claim of this corollary, right? So we multiply by adjacent transpositions k times, so the sign of the parity will switch k times, and then we get that the parity of the product is equal to -1 to the power of k, where k is the number of adjacent transpositions in this factorization. Now we can state the fundamental theorem about the properties of the parity. So theorem that the parity of the product of two permutations is equal to the product of parities. So this tells us that if both sigma and mu are even, then their product is also even. And if one of them is even and the other is odd, then the product is odd. And if both factors are odd, then the product will be even. Let's give the proof of this theorem. So we know that every permutation may be factored as a product of adjacent transpositions. So we're going to factor sigma as the product T1 times T2 times Tk, and mu as a product of S1 times S2 times Sm, where so Ti's and Sj's are adjacent transpositions. So then, by this corollary, so the parity of sigma is equal to -1 to the power of k. So the parity of mu is equal to -1 to the power m. And the parity of the product, sigma times mu. So now if we take the product of these two, then we get a factorization into adjacent transpositions with k plus m factors. So this means that this product will have parity of -1 to the k plus m, which is equal to the parity of sigma times the parity of mu. And this proves this theorem. Let us see how we can calculate the parity of a permutation in a more efficient way, especially if this permutation is long. So first, let us state the following lemma, that every transposition AB is odd. Well, we know that an adjacent transposition is odd because an adjacent transposition will have a single inversion. But here we are saying something more, that if we take any transposition, then this will be an odd permutation. So let us give a diagrammatic proof of this. So suppose we have A and B, right? So what does this transposition will do? So it will send A to B and B to A, while all other elements will not change, so they go to themselves. Now, let us count the number of arrow crossings here. So what we see is that each blue arrow will either not cross arrows from A and B at all, or it will be crossed by arrows from A and B twice. And so this means that we have a single crossing of arrows from A to B and B to A, and then an even number of crossing elsewhere. And so what we see is that the number of arrow crossings here is odd. And so this tells us that the transposition AB is an odd permutation. Our next theorem says that the parity of a cycle of length k. So if we have a cycle A1, A2, ... AK is -1 to the k minus 1. So which means that cycles of even length are odd and cycles of odd length are even. So this is consistent with our previous lemma. So that said that a transposition, which is a cycle of length 2, is odd. So the proof of this goes by induction on K. And the basis of induction is the case when K is equal to 2, right? Because this is the smallest possible length of a cycle. And the case of K equals 2 is already covered here. So this lemma establishes the basis of induction. Now, so what is the step of induction? So we make an induction assumption. So we assume that a cycle of length K minus 1 has parity minus 1 to the K minus 2. We make the following claim, that the cycle A1, A2, AK minus 1, AK may be factored as a cycle A1, A2, all the way up to AK minus 1, times the transposition AK minus 1, AK. Now, let us compare these two permutations. Now, A1 under the left-hand side will go to A2. And so here, so the first transposition will not move A1. And A1 will go to A2 under the right-hand side as well. And so this will be true for all A's up to K minus 1. Now, in the left-hand side, AK minus 1 goes to AK. So what happens in the right-hand side? In the right-hand side, the first factor will move AK minus 1 to AK, and the second factor will not move AK. So this means that AK minus 1 goes to AK. How about AK? On the left, AK goes to A1. And on the right, first AK goes to AK minus 1, and then AK minus 1 sends it to A1. So as a product, in a product, AK will go to A1. And if we take any element B, which is not in this sequence, then it will not be moved neither by the left-hand side nor by the right-hand side. And this shows that cycle of length K factors in the following way as a cycle of length K minus 1 and a transposition. Now, to compute the parity of a cycle, we apply our theorem about that the parity of the product is the product of parities. And so what we get is that the parity of this cycle A1, AK is equal to the product of parities of the two factors in the right-hand side. But by induction assumption, the parity of cycle of length K minus 1 is equal to minus 1 to the K minus 2. And the parity of a transposition by our lemma is equal to minus 1. And as a result, we get that the parity of a cycle of length K is equal to minus 1 to the K minus 1. And that's exactly what we wanted to prove. Let us now do the following exercise. So compute the parity of the following permutation sigma in S12. So sigma is the following. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And say 1 goes to 6, 2 goes to 11, 3 goes to 7, 4 goes to 1, 5 goes to 12, 6 goes to 2, 7 goes to 3, 8 goes to 10, 9 goes to 9, 10 goes to 4, 11 goes to 5, and 12, what's left? 1, 2, 3, 4, 5, 6, 7, 8. All right, okay. So now, so this is a long permutation, and it has a great number of inversions. Counting inversions here becomes somewhat ineffective. So instead, let us factor this permutation into independent cycles. So, okay, so let us do this. So 1 goes to 6, 6 goes to 2, 2 goes to 11, 11 goes to 5, 5 goes to 12, 12 goes to 8, 8 goes to 10, 10 goes to 4, and 4 completes the cycle, it goes to 1. Right? So, but that's not all. So what is left out? So, okay, so we have 3 goes to 7, and 7 goes to 3. So this completes the cycle. Now, does this cover everything? So we have 1, 2, 3, 4, 5, 6, 7, 8. Okay, we don't have a 9, so 9 is a cycle by itself. And now we have 10, 11, and 12. Right, so now this is a complete factorization of sigma into a product of independent cycles. So this was easy to do. Now, let us look at the length. So here we have length of this cycle is 9. And so here we have length 2. Well, and this one is identity, so we can forget about it. Right, and so then we get the following result, that the parity of sigma is equal to the product of parities of factors. But the first factor has parity -1 to the power 8, right? So because the parity of a cycle of length 9 is equal to -1 to the power 8. So cycles of odd length are even, and cycles of even length are odd. So this means that the second factor has parity -1. It's a transposition. And the identity element is even. And so what we see is that this permutation is odd. And so this way of computing the parity of a permutation is more efficient than computing the number of inversions.
What you see here is the grandfather of PlayStation and Game Boy. This is called the 15 puzzle. It was invented in the 1870s in the United States of America, and in the winter of 1880 it went viral. In February, this craze took over New York and stopped nearly all business in the city. Everybody caught the bug and were playing this game. By March, this fever reached Canada and it took over Europe in summer of 1880. Here is how you play this game. You have a 4x4 grid filled with 15 tiles, and one space is left empty. You first scramble the board. Once the board is thoroughly scrambled, you try to put the tiles back in their original places. done. In a particularly challenging variation of this game, instead of scrambling the board, you just switch the tiles 14 and 15 and try to solve the puzzle from this initial position. The hype about this puzzle was fueled by the fact that a substantial prize was offered for solving this particular challenge. People rushed to solve this puzzle, and there were many who claimed to have done it, but just did not write down the solution. This craziness went on in spite of the fact that a year earlier, a paper was published in the American Journal of Mathematics proving impossibility of solving this particular challenge.
Let us use permutations and prove that the challenge of swapping 14 and 15 cannot be solved. That is, if we start in the standard configurations and apply valid moves, we cannot come to positions where 14 and 15 are interchanged. First thing we want to do is associate a permutation from S16 to each board position. For example, for this board position, we associate the following permutation, which says that the tile from position 1 went to position 16, a tile from position 2 went to position 1, a tile from position 3 went to position 6, and so on. The empty space, which we interpret as a tile number 16, is now in position 11. Let us analyze how we make admissible transformations of a board. For example, in this position, the empty tile is in place 11. This means that on the next move, we can place tiles from positions 7, 10, 12, or 15 in position 11. The empty tile will then move in the corresponding square. This means that a single move corresponds to a transposition involving empty tile. Let us record this. So if the current board position corresponds to a permutation sigma with sigma of 16, say, equal to 11, then a subsequent board position is one of the following. We are allowed to multiply sigma on the left by one of the following transpositions. So it could be 7, 11 times sigma, then 10, 11 times sigma, 11, 12 times sigma, or 11, 15 times sigma. So we see that performing one valid step corresponds to multiplying sigma on the left by a transposition involving the current position of the empty tile. Suppose we start in the standard configuration and come to a configuration where 14 and 15 are swapped. The tile 16 has returned to its original place. So let us look at the trajectory of the tile 16. So it will go up, down, left, or right. But eventually it will come to its original position. So this means that the number of up arrows in this trajectory is equal to the number of down arrows in this trajectory. And the number of left arrows is equal to the number of right arrows. So this tells us that the total number of steps is even. So we get that the permutation that we need to implement, and this is a transposition of 14 and 15, is equal to the product of transpositions tau 1 up to tau n but the number of factors here is even, because each valid move will displace the empty tile in the adjacent square, and the number of arrows in this trajectory is even, while each transformation, tau j, is itself a transposition. Which involves swapping an empty tile with an adjacent tile. But now compare the parities. On the left, we have a single transposition, which is odd. And the parity of the transposition on the right is -1 to the power n. And n is even, so we see that the transposition on the right is even. Thus, this equality cannot possibly hold, and the challenge of swapping tiles 14 and 15 is not solvable.